This example explains how to use the Altair Embed application to control a PMSM motor in an open-loop fashion. This example will focus primarily on the PWM and ADC blocks. For the target, we'll be using the Texas Instruments F28069M launchpad board target, also known as the Piccolo, a Teknic M 2310P low-voltage servo motor with built-in encoder, and a Texas Instruments DRV 8301 inverter board. We'll approach this example using two models, a source model to generate the out file and a debug model to execute the out file on the target and write signals back to the host PC in real time. The source model is set up to simulate from 0 to 10 seconds in increments of 0.0001 seconds and to run in real time. Diving into the motor control block of the source model, there are three PWM signals being produced in open loop. The motor angle, theta command, is set to a ramp signal. The flux command, ID ref, is set to 0, and the torque command, IQ ref, is set to 0.15 amps. The open loop control produces three PWM signals, labeled PWM-A, PWM-B, and PWM-C. These signals have been converted to 1.16 scaled integer format in the blocks entitled Scale. Within the PWM block, we are using channel A of three PWM building blocks. Let's look at the configuration of the first block. There are three basic areas you need to configure in the PWM block: the time base, the action qualifier, and synchronization of the ADC with the PWM. First, we'll look at the time base setup. We set the count mode to up-down. This is a good choice for motor control applications because it's easy to synchronize the ADCs that are sensing motor current to sample at the halfway point. The timer period is used to define the PWM carrier frequency. A good frequency is 15 kHz. We have adjusted the timer period to 3000 CPU cycles, which is equivalent to 15 kHz. The action qualifier setup. First, make sure the GPIO pin is set correctly, in this case to GPIO 0. CMPA for ePWM-A is set to Z equals nothing, up equals 0, and down equals 1. This means that when the normalized value of the PWM counter, which counts from 0 to 3000 at 15 kHz, passes from less than to greater than the duty cycle command, the PWM will be set to 0. And when the PWM counter passes from greater than to less than the duty cycle command, the PWM will be set to 1. For an up-down count mode, a complete PWM cycle requires 2 times the period, or 3000 counts. The halfway point is PRD counts. When the PWM counter reaches the PRD value, a pulse named SOCA is produced. This pulse is used to trigger the three ADCs to read the current values. This model uses three ADC blocks: ADC result 1, ADC result 2, and ADC result 3. They are synchronized with the PWM block using the ADC config table located under Embedded, Piccolo, ADC. In the config table, you'll notice that each of the three ADCs is being triggered by the SOCA pulse from ePWM1. We have also allowed 12 CPU cycles to get a better average value for each current. We'd like to look at several of the signals from the target as the open loop control is executed. I've wired 6 signals: the theta command value, the measured theta value, an index signal coming from the built-in encoder, and the 3-phase currents. Let's code-gen our source model and see how it works. After selecting the compound block, select Tools, Code-gen. Ensure the Use Selected Compound Edge Pins for Data Exchange is selected. Defaults for the other settings may be used at this time. Select the Compile button. The compile results are presented in a DOS window. Select any key to acknowledge the DOS prompt, then select Quit. Now we're ready to run our code on the target. Here I've opened the debug model. I will click Go to start. You'll observe the out file being transmitted to the target, then it will begin running. I've started with the open loop controller turned off. Let's turn it on. Looking at the lower three plots, we can see the three current waveforms evolving at the same frequency. The quantization is due to the bandwidth limitation of the JTAG interface we are using.